Good morning. So I am Iryna. I am a third-year PhD student in the chair of Claire Pagetti. And today I will present to you a glimpse of my work on the certifiable and efficient implementation of machine learning algorithms on avionics systems. So we are particularly interested in the implementation of offline-trained, feed-forward deep neural networks. So we will look at the output of the design phase of the neural networks. That is the trained and optimized model that we call inference model. But to implement the inference model, we first have to bridge the gap between the machine learning and the avionics domains. In particular, the avionics systems, they are subject to reach the certification process. And if you look at a subset of these certification requirements, we are especially asked to ensure the traceability between the specification and the final function, and to be able to compute the tight worst case execution time of our embedded function. And moreover, we are working on embedded targets. So we have to be able to deliver good performance in mostly single core platforms. Okay, those are properties and conditions that are not easily met in the existing machine learning frameworks, both for design and both for training, and also for training. So that's why we developed Aceton, that stands for Avionics C Code Generator for Neural Networks. It is a tool that from a model description of the inference model, it automatically generates a C code that preserves the semantics of the inference model, and that we could also obtain the worst case execution time bound using static analysis. And then we also implemented this output of Aceton on an ARM core to obtain a measured execution time and evaluate performance. We tested it in several use cases, real-world use cases. So neural networks used for classification and for image processing. And we also compared it with the state of the art. And then we verified that the avionics requirements, they were met, but the convolutional layers, especially the implementation that was done within Aceton, and especially the convolutional layers, could be improved. So what was the idea? The idea was to reduce the convolutional layers execution time by implementing it as a matrix multiplication. So that's what we call gen-based convolutions, gen for general matrix multiplication. So to do that, we basically have to modify a little bit the original entries of the convolution. And that is a good idea because the HPC community has been working on improving matrix multiplication for years. But again, the existing libraries of the HPC community, they are not built with avionics constraints in mind. So we ended up having to write our own routines. So at the end, we had this. We were able to provide a compliant C code for implementing matrix multiplication. We proposed several variants that would allow different matrix configurations. We also had a version where we could use pointers to avoid building this expanded matrix in memory. And then after this phase, we managed to reduce the measured execution time by 50% on average. But to go further on optimizing matrix multiplications, we have to take into account the hardware specificities. So let's consider our target has only one core, and we are interested in the main memory, the cache memory, and the vector registers that are implemented in the vector extensions, implemented by the vector extensions. So for computation to happen, data has to go from the main memory to the registers, going through the caches in the way. The faster it is to access data, the smaller is the component. So what is the idea? The idea is to block the original matrix in smaller submatrices so they can reside in the different levels of memory, so the caches and the vector registers, and then computation can happen faster. So, as I said, we are interested in vector registers, which are a special kind of registers that can operate on multiple data at the same time because they are organized as vectors. Actually, using vector registers is not that difficult, but when you have to be compliant with the avionics constraints and not use compiler optimizations, for example, it gets a little bit more difficult. So we have to programming a very low level to guarantee the correctness and the traceability of our implementation. By doing this vectorized implementation without compiler optimizations, we managed to reduce the measured execution time by 98% on average. That was really huge. An example that we have is, for example, to compute the green block of matrix C, I'd like to use the same block of B for different blocks of A, like this. The problem is that, contrary to vector registers, we cannot explicitly load data into cache. We can only expect that because a block of matrix fits in the cache, it will remain there. But we want to be more precise than that. And what we did, so we would like to have an upper bound on the number of cache misses and improve the worst case execution time estimation when executing a matrix multiplication. So what we did was we came up with some analytical formula to say how to correctly choose the size of those blocks so we can bound the number of cache misses and guarantee that a block B, for example, won't get evicted from cache before while it is still needed, right? So we compared we evaluated our formula by implementing our approach, and we observed that compared to the state of the art, we managed to reduce the number of cache misses by 60%, which was really cool. So to conclude, we are able to automatically generate a functional equivalent and a time predictable C code that corresponds to an inference model. We are able to provide this efficient implementation that is compliant with the avionics requirements. We proved it to be competitive with the state of the art with respect to our defined criteria. And some perspectives that arise from that is that we could be able to cover a wide range of inference model architectures, some of those new models that are coming up. And we could also extend this optimized implementation to do it automatically and cover a different number of targets, hardware. Okay, thank you for your attention.
Thank you very much, Iryna. Questions? Yes, Florent.
Yes, I didn't detail that, but that was a criteria that we observed. And then we verified the semantic preservation by comparing the output of our C code with the output of the training framework. So yes, we verified that the errors they are bounded, and they can be explained by the differences in float point operations.
I have a question. So you mentioned so you are performing this GMM operation, right? And you said that you have to take into account constraint from the application. So for this matrix multiplication, what are the constraints? You avoiding overflow, or what are the kind of constraints that you have to take into account?
When I mentioned the constraints was basically because in the avionics domain we cannot use, for example, compiler optimizations, and that's basically on what the HPC, the high performance computing community relies on. So basically, you have to. The constraint is that we cannot do what they do, but you have to be as performance as them. Yes.
And then when you mention saving. You are better. Is it a comparison with this HPC implementation that use the compiler options, or or you managed to do better than those libraries, the BLAST libraries that are available? Or?
No, not really. Actually, we are better than our original implementation, of course, and that the 90% is related to that. And the reduction in cache misses, yes, it was using their parameters, because they don't really care about bounding, about having this really tight bound on the number of cache misses. They only want to go fast.
Okay, thank you everybody. So now